I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where we are going to look at second order linear homogeneous differential equations where you would expect complex conjugate solutions. What you see right here is a template that you would utilize when two different real solutions arise, but this template here will be modified to generate the templates you would use for complex conjugates. You know, complex conjugates are this: a plus and minus bi. There are two different solutions, a plus bi and a minus bi. Very quickly, as an example of a second order linear homogeneous differential equation where you would expect complex conjugates, we are looking at only one example in this video. Our focus is the template and the presentation of the solution. In another video we can do practice. You know what you're looking at over here is this. It looks something like this. You do a substitution, y is equal to e to the rx. The first order derivative is re to the rx. The second order is r square e to the rx. You bring these in. This right here is equal to y single prime. That's equal to y double prime. Bring the substitutions. I have a double prime here, so it's r square e to the rx plus 2y, which is e to the rx equals 0. Isolate e to the rx and you'll have r square plus 2 equals 0. You can take this on the other side and zero it out. You essentially have r square plus 2, which is a quadratic equation, x square plus 2, a parabola directed upwards, vertex 0, 2. It's never touching the x-axis, so obviously you will have complex conjugate and or imaginary solutions. R is equal to plus and minus root of minus 2. Simplified, plus and minus I root 2, which is 0 plus and minus I root 2. Here are your complex solutions. How would you present it? In what format? Our format is this: y is equal to e to the power of ax. And look, lowercase a, as you see right here. Here's my a. Constant cosine bx. Here's my lowercase b right over here. Plus another constant, sine bx. Here's my b over here. But you see, that template does not have an imaginary number in it. The imaginary number goes away. This here is my b, that's my a. When you bring that in, this solution into that form, you have e to the power of 0x. You'll have a cosine root 2x, because b here is equal to root 2, plus b sine root 2x. That's your solution. You can clean it out. E to the power of 0x is meaningless. It's just a cosine root 2x plus b sine root 2x. That's my solution for this differential equation. Our goal now is to demonstrate how does this template come about. Why does this template behave or look the way it does? It's gonna come obviously from this template right here and a lot of manipulation, but I will show you all of that. Everything will begin with you having a plus and minus bi complex conjugate, which you're gonna bring into this template right here. Y is equal to a e to the power of a plus bi x. That's one of your solutions, and obviously the other solution is the conjugate of this, plus be exponent a minus bi x. That's what it is. Open up everything with the x and the powers or the laws of exponents. Y is equal to a e to the ax e to the bix. If I combine this, I should have that. It's just laws of exponents at work. Plus b e to the ax e to the minus bix. That's what you have. Isolate e to the ax. Y is equal to e exponent ax. You'll have a e to the bix plus b e to the power of minus bix. Now we're beginning to take the form of what you see over here. From this point onwards, it's a few things coming into play. You have the Euler's identity coming into play. E to the I theta is equal to cosine theta plus I sine theta. That's gonna be the procedure which will help you eliminate the imaginary number and get into your solution form. Another identity you need to worry about is this: cosine of a negative angle, because this is an even function, is equal to cosine positive. Sine of a negative angle or a value is equal to minus sine, because it's a odd function. This is even, that's odd, so it's behaving the way it is. Those three identities are going to come into play over here. You're going to expand this out using the Euler's identity. Y is equal to e to the ax, a. Now let's expand this out. Cosine theta, which is bx, plus I sine bx. What's my theta over here? In these instances, it's equal to bx or it's equal to minus bx. You see that? All of that is coming into play. Now let's do this part right here. B cosine minus bx plus I sine minus bx. And there it is. We can make sure we have all of our parentheses closed, and we'll close them out. What can we do from here? You can come over here and bring the identities into play. This one and this one. Cosine of that minus is a positive. This minus can come right here and make that into a minus because it's an odd function. From here, you want to start isolating. I have a cosine bx, I'll isolate them. Cosine bx. It goes into this expression a times, it goes in this expression plus b times. I have a plus. I'm going to isolate ai sine bx. It's going to go into this expression a times. It's going to go in this expression minus b times. Here is where everything becomes interesting. We do a substitution to help algebraically manipulate what we have to get to where we need to be. A is equal to b is equal to 1 over 2 for this part right over here, because there's no imaginary component. From this part, our substitutions will be a little different because we have an imaginary number we need to worry about and get rid of. A is equal to minus I over 2, b is equal to positive I over 2. Because here we have an imaginary number, I'm doing I over 2. Here we don't have imaginary number, so I'm using positive 1 over 2. All of these values for a's and b's will come into play, and we'll bring them here. Y is equal to e exponent ax. I have a cosine bx. A plus b is a half plus a half, which is a 1. There's no need to write a 1, it's meaningless. Plus I have a sine bx. A minus b is a minus I over 2 minus I over 2, which is a minus I. This minus I is going to multiply with this, and you'll have a minus I square. If I square is equal to minus 1, minus I square is equal to positive 1. And that's exactly how your I, your imaginary component, will go away. And this minus I and minus I square will eliminate because it's equal to 1. You'll have y is equal to e ax cosine bx plus sine bx, and I'll close it. The only thing missing here are now my constants, which would come about because you're dealing here with the second order linear homogeneous differential equation. It's second order, so you must have two constants, and it looks exactly as that, and the derivation procedure for this template is complete. Remember, this is the template you're using when you have these type of solutions expected from your quadratic expression that you have converted your differential equation into. Everything being arisen from this template, which you would have used for two real solutions, but it helps modify it for two imaginary or complex solutions in this template form. In the future video, we're going to be actually doing examples. So see and understand what you have from this video. It will help for the next video. Have a good day. Bye.